Hello everyone, welcome to the third live section of this course, which is Quantum Transport. I'm Gitanjali, I'm a PhD scholar from IIT Delhi, and I'm the TA for this course. So, as I said before, in for each week, we'll first go through the concept that has been taught during the week, and according to the concept, we'll try to solve few numerical as well as the some conceptual problems that will help you to understand the concept more, and also it will help you to solve the weekly assignment. So we are in third week where we for in first two in first two classes we go through what are the different types of fabrication processes, and then we went on to study what are the quantum Hall effect. So let us start our session. So if you see the regime for the quantum ballistic transport. So for this regime, we need the Fermi wavelength. It should be in the order of the device length, which is which should be less than the mean free path, which is elastic mean free path or the phase coherence length. So if you take the example like for gallium arsenide based two-dimensional system, the elastic mean free path, it is in the order of 10 micrometer, and for let take white color. Okay. And for the phase coherence length, it is in the order of 1 micrometer. Similarly, for silicon, the elastic mean free path, it is 1 micrometer, but the phase coherence length, it is less than 1 micrometer. So that means to see the quantum ballistic transport, we need devices which are less than this dimension, which is in the order of micrometer. So to see the quantum transport phenomena, we need devices in the order of some micron. So for this, what we can do, we have two types of method. One is the top-down approach, and another one is the bottom-up approach. So for top-down, so it means we are basically starting from a macroscopic medium, and gradually we are refining that macroscopic medium to get our design, which has a specific dimension. So this is top-down approach. For top-down, it is widely scalable, and the precision is also controllable for the top-down approach. For the bottom-up approach, so we start from the atomic dimension, then we gradually grow the material on that medium to get our desired design. So relative to the top-down approach, the bottom-up approach, it's low cost, and it can have a dimension which is much lesser than what we can get in the top-down approach. But the main demerit of this uh, bottom-up approach, it is not scalable. So now let us look at one of the method to design our device that we want to see the quantum transport. For that, so the most widely used. So these are some. Let me skip this slide. So the most familiar technique to design our structure, it is to use the photolithography. So it basically uses light and a mask system to design our structure of given dimension. So to give a brief overview, so basically what we do in photolithography, we deposit the regist, which is kind of a polymer And one of the example that you can take is PMMA. So we deposit the resist on the substrate or the silicon wafer that is widely available. So we deposit the resist on that substrate. Then what we do, we use the mask. So this is the coating. First, we have the coating stage. Then, depending on the design of the device structure on the substrate, we design a mask and we place the mask in different modes. So there are different modes that we'll see in the next slide. So we place this mask on the top of the photoresist. Maybe it is in contact with the photoresist, or maybe it is at a distance, or maybe the mask, maybe the design on the mask is projected onto this photoresist. So depending on the mode, next what we do, we shine the optical radiation on this mask. Okay. So what will happen whenever these photoregists, these are sensitive to the optical radiation. So depending on the type of photoregist, we'll see different types of pattern uh, which can be made on the substrate. Okay, so there are two types of photoregist. One is positive photoregist and another one is the negative photoregist. For positive photoresist, what will happen whenever this photoresist get exposed to the optical radiation? Then the exposed part, so this becomes sensitive and this become the solubility of this area become they increases the solubility will increase whenever it get exposed to the optical radiation. And what will happen, so when we use some solvent to remove this photoresist, this exposed part will be removed after the in the develop stage. So this is for the photoresist where the exposed part will be removed. For the negative one, it is quite contrast to the positive case. In negative, the area which is not exposed to the optical radiation, they become more sensitive to the solvent that we'll use. And what will happen, the solubility of this unexposed area will increase. And whenever we use the solvent in the developed stage, this unexposed area will be removed in the developed stage. So after doing the develop stage, what we will have a structured regist. In one case, we have a pattern like this. In another case, we have the pattern which is complementary to the pattern we have in the positive photoresist. Then afterwards, after the develop stage, what we can do, we can each the sample that we get to a given dimension using different types of method. There are different like wet etching and wet etching, and there is also dry etching. So using that, we can etch the material, or what we can do, we can also do a metallization where we deposit metal on the surface of this patterned photoresist. So we can do whatever we want to do. Like we can either etch the surface, the structured photoresist, or we can do a metallization, which is explained in detail in this figure. So after etching, we will remove the excess part. We'll remove the photoresist part in the using the stripe. Okay. So this is the overview of the photolithography stage. Next, we have what are the different types of modes of a optical lithography, depending on the distance between the mask and the substrate. So there are three types of modes. One is the contact mode, and next is the proximity mode, and the third one is the projection mode. So for contact mode, it is quite evident from the name that it is the mask in this case will be in contact with the substrate. So mask is in the contact of the photoresist. Sorry. So in this case, we have one-to-one magnification, and the resolution that we can get is in the order of 0.5 micrometer. But the main disadvantage is that whenever, because the mask is in contact with the photoresist, we can't use the mask for further application. So once we are done with the steps by using the mask, then the mask can no longer be used because it is in contact with the photoresist, so it degrades its performance. In the proximity mode, what we have in there is a gap between the photoresist and the mask. So magnification is one to one, but and also the resolution is it is bit larger than it is two times of what the resolution we have in the contact mode. So for this proximity mode, it is in the order of 1 to 2 micrometer, and the main effect is that we'll see a diffraction effect, which will limit the accuracy of the pattern transfer from mask to the substrate. So this is approximative. For projection mode, the resolution is quite higher. It is in the order of 0.007 micrometer. And what we do in this case, instead of making the mask at a distance from substrate or making the mask in contact with the photoresist, here we project the image of the mask onto the photoresist sample. So using this objective lens and condenser lens. So in this case, because of this, there will be high resolution in the order of 0.007 micrometer. And we can use the photoresist further because we are making the images on the sample. We are not directly using the mask on the substrate. So because of that, the reproducibility of this step is quite higher. But the main disadvantage, it is extremely expensive. Also, it requires complicated equipment. And also, similar to the proximity case, there will be diffraction in projection mode. So the new techniques also, we have a maskless writer where we use DMD chip to write the pattern on the sample. So these are some of the example of some of the SEM images of a pattern that we made using photolithography. So let me go to the further slide. So we talk about the diffraction effect for contact and some soft contact mode, and also the diffraction effect will be there in the projection mode. Most of the time, we want that whatever design is there on the mask, it should be the design should be exactly matches whatever the design we have on the substrate. So, but most of the time it is not the case. We have the diffraction effect, like we have near field diffraction for the case of contact and subcontact mode, and we have the far field diffraction effect for whenever you use the projection mode. So what they will do, they will spread out the beam and spray because of the bending of the light, the sharp design we want. Let's say we want this rectangular design, so it will get sprayed out, and when we increase the distance, the sprayed out becomes more and more. So because of this, the some pattern transfer from mask to the photoresist, it becomes sensitive to the gap between the photoresist and the mask. And this is one of the uh, equation or one of the relation that you can use to find out what is the minimum features size that can be resolved or that can be patterned on the photoresist use in the contact and sub-contact mode. You can see the feature size. It is related to the wavelength of the optical radiation, and it depends on the gap which is present between the photoresist and the uh, photoresist and the mask that we have. And when we increase the gap, the feature size that can be resolved, it also increases. So that means the resolution decreases. Okay, so this is about the soft contact and the contact mode. Next, we have the effect of far field radiation in the projection mode, and this is mostly because of the AVE limits. So, using the AVE limit, you can find out what will be the minimum feature size that we can resolve or we can pattern on the substrate using this projection mode photolithography. And these are the relation that we have. For using the Abbe limit, we can find out what is the minimum feature size, which is K1 times lambda by Na. So it depends on the numerical aperture. And also the depth of focus, that is the vertical resolution for this case, we have this relation, that is sigma is K1 times lambda by Na square. So Na is the numerical aperture. We can also write it as n sine theta. Theta is the angle at which the ray incident on this substrate and is the refractive index of the medium. So this is about the resolution of the photolithography using either subcontact mode or contact mode or the projection mode. Next, what we have, and this photolithography techniques, it will design the object size that we will get in this photolithography. It is on the in the order of micrometer. So next, what we have is the electron beam lithography, where instead of using the light, we use electron beams, high energy electron beams, to pattern the surface to get a desirable feature size. So in these are the schematics. So we use high energy electron beam to write the nanoscale pattern on the surface of the substrate. So this is the schematic of the electron beam process, where we have electron gun where electrons are emitted uh, from the cathode. Then the electron beam goes through a optical stage where it is collimated and it is focused onto the sample. Also, we have scanning coil where we can deviate the path of the electron beam to get a desirable pattern. And also to see the surface topography, to see the design that has been made on the surface. We can use the secondary electron or the backscatter electron. We can collect it, and depending on the data, we can image the surface topography. So in most of the case, the resolution for this case, if you recall, for photolithography, the resolution, it depends on the wavelength of the incident radiation. In addition to the gap, it also depends on the wavelength. But for electron beam lithography, it mostly depends on the resist properties as well as the forward scattering and the lateral diffusion of the secondary electron. So in the secondary electron, these are the ones which controls the resolution. And when so let us see. So these are some of the interactions process that can happen whenever the electron beam heat a specimen. So we can have backscatter electron, or we can have secondary electron. We have OJ electron, or we can have the X-ray emission from the surface. So, but for the more for our case, we are more interested in what is happening to this secondary electron and backscatter electron. So, as I said, the electron beam lithography, it doesn't depend on the kind of does not depend on the wavelength of the electron beam that we are incidenting on the surface. So it mostly depend on the lateral diffusion as well as forward scattering. So so what this means is that whenever the electron beams are, whenever it hit a sample, so we have a spot size of the electron beam that is hitting the sample. But in reality, what we have a spot size which is greater than the spot size we are using. So in that case, the pattern transfer will be quite, it will be slightly different. And this happens because of the lateral diffusion. So whenever we let's take an example. If we use a beam of size 2 nanometer, then the effective area which is affected by this 2 nanometer beam is it is greater than the size we are using here, which is 2 nanometer. And this is because the secondary electron diffuse by scattering with other scattering centers. So this because of this lateral diffusion of this secondary electron, the feature size will now become different. So the resolution limit for this for this electron beam lithography, it is mostly decided by of the lateral diffusion as well as the forward scatter. So this is about the resolution. And the next difference that we have from photolithography to electron beam lithography is the charging effect. In photolithography, what we use a optical radiation, which are chargeless particle. So there is no concept of charging effect on the substrate whenever the optical radiation hit the sample. So it doesn't depend what kind of substrate we are using, like whether it is conducting or insulating, or it is whether it is a semiconductor or not. But if you look at the electron beam lithography, we are using electron beam which are negatively charged particle. So if we use insulating substrate there to pattern the design on the substrate, what will happen? There will be a charging effect because this is an insulating substrate, so the charge will accumulate on the upper surface of the substrate, and that accumulated charge they will deflect the incident electron beam that is hitting the surface. It will deflect it, and because of the deflection, the pattern transferred will not be that accurate. So there will be a pattern distortion whenever we have a charging effect. So, for most of the cases, whenever we have a conducting sample, what we do, we use resist which are insulating, but the charging effect won't be there if the thickness is less than 500 nanometers. So it will directly interact with the conducting substrate that we are using. So this we have to keep in mind that we have to keep the thickness of this resist below 500 nanometer. And besides that, if let's say our substrate it is a insulating, so for that case we can use a conducting layer on top of this or on beneath of this resist to eliminate the charging effect. And this conducting layer, there are different types of metals that we can use. Maybe we can use aluminum, titanium, chromium, or gold. But for most of the cases, we use the lighter metal because they causes because the forward scattering there is quite less than the heavier metal, which is gold. And also this lighter metal, aluminum and titanium, we can easily remove it by using if you dip the sample in a diluted hydrofluoric acid. So this is one of the effect that we have to keep in mind whenever we are using the electron beam lithography. So we have to keep in the mind of charging effect. So if we are using a uh, insulating substrate, we need a coating, conducting layer coating there. Or if the substrate is conducting, we can proceed to pattern the surface. And also we have to keep in mind we have to take a resist thickness of less than 500 nanometer. So also, in some of the situation, what we do to speed up the process, we use a combination of photolithography as well as the electron beam lithography. So what we can do, we can the pattern which doesn't require precising, we can proceed to pattern it on using the photolithography. Then uh, the more smaller dimension, we can use the electron beam lithography to pattern the design on the substrate. So we can use a combination. In the next case, we also see what are the metallization and lift up process and what is the pattern we can get in the metallization lift up process for both photolithography as well as the electron beam lithography. So the profile, it can be of three types. One is undercut profile or lift up profile, and other one is the overcut profile, and next one is the vertical profile. So these are the three types of profile that regis profile that we can have in the development stage. So, but the regis profile which will give more accurate design is the undercut one, because in when you lift off, then the pattern won't be distorted in the undercut profile. Uh, okay. So this is all about the metallization. Then these are some of the techniques that we can do to deposit the metal. We can use thermal evaporation, where we can place our desired metal on the boat and we heat the boat. So because of the heating, this metal will get melt and they will get evaporated, and after evaporation it will get deposited on the sample, the structured photoresist in the metallization state. And the other type of is we have the plasma sputtering, which is kind of similar, but it also gave a uniform metallization as compared to the thermal evaporation. So, as I said, etching, it can be of two types. One is the wet chemical etching, where we use a solvent to etch our sample. So wet chemical etching, it is isotropic because it is because of the chemical reaction. So because of the chemical reaction, we'll see isotropic pattern whenever we use the wet chemical etching. For dry etching, it is not isotropic, but it is highly directional. So if you want to mm, uh, SAR, or if you want a SAR profile, then we can go on to use the dry etching technique. Okay, so these are the some of the microscopic images of the gated device fabricated using either electron beam lithography or the photolithography. In the towards the last part of the lecture, we see what is the quantum Hall effect. So we know for now we know what are the different types of technique that we can use to fabricate our design. Now let us see after designing what are the quantum effects that will happen in our device if we operate it. So one of the effect is the Hall effect. So Hall effect, it is nothing but it is the production of a voltage in a conducting sample whenever we place the sample in a transverse magnetic field. So if you look at this diagram, so this is the schematic of a Hall effect sample. So the current is flowing in this direction because of the applied voltage. And now we are applying a magnetic field in the transverse direction, that is in the Z direction. So because of this transverse magnetic field, the charge carriers now they will experience a Lorentz force. In addition to the force because of the electrostatic potential, because of the battery that we are using or the any type of driving force which drives this electrical current. In addition to that, we have the Lorentz force, and this Lorentz force will deviate the path of this charge carrier. And because of this deviation, there will be charge accumulation on the edges of the sample. And because of this charge separation, now we'll have a voltage across this transverse direction. So this voltage is nothing but the Hall voltage because of the applied transverse magnetic field. To quantify the what will be the Hall resistivity and what will be the longitudinal resistivity for this case, we can use the Drude model. So we can match for the steady state, we can match the momentum lost should be equal to the momentum received. And the momentum loss, according to the rules, we can write it as mvd by tau m. Vd is the drip velocity, and tau min is the scattering time between two conjugative collision. And the momentum received, it is due to the electrical force, which is E times the electric field, and also the Lorentz force, which is Vd times Vd cross B. So if we make a rearrangement and if we use this component of electric field, drip velocity as well as the transverse magnetic field, so we will get a matrix like this. And if we rearrange it further, then we will get a matrix which is kind of similar to the Ohm's law that we have seen earlier. So this matrix we can write it as E equal to rho times J, where rho is the resistivity, J is the current density, and E is the uh, electric field that is driving the electrical current. So if you now look at the component of this matrix, so we have in the presence of magnetic field, we have two of diagonal term, and also we have a term which is diagonal term which is a constant. This off diagonal term, it depends on the magnetic field strength. It changes with the strength of this magnetic field. But for the diagonal term, these are constant. Okay, so we can now term it the constant part. This is the normal resistivity that we have seen without any application of the magnetic field. This we have seen earlier. But when we applied a transverse magnetic field, now in addition to this diagonal term, we have off diagonal term, which is rho xy or rho yx, which is b by n. So rho is directly proportional to the strength of the magnetic field. Also, it is inversely proportional to the uh, density of the charge carrier. And if you, according to this relation, if you plot the graph between the Hall, the potential difference or the Hall potential, then we see that as we increase the magnetic field, the Hall voltage also increases linearly. Similarly, this that if we do the same treatment to a 2D electron gas system, like the surface of a gallium arsenide or aluminum gallium arsenide. So these are the 2D systems, 2D electron gas system. So what will happen because there will be a quantum confinement because of the bending of the conduction band and the valence band. What we'll see that instead of a linearly varying Hall resistivity, now the resistivity changes in a step-like manner. So this is the quantum Hall effect. So, this is the first experiment that proved the quantum Hall effect in a silicon MOSFET. So, for this silicon MOSFET, the conduction band bent downward because of the charge transfer at the interface. And when the charge carriers occupies this because of this bending, so there will be a quantum confinement of this charge carrier, and we'll see a discretized energy level for this quantum well. And this discretized energy level, they will discretize the Hall resistivity in terms of h by e square. So instead of b by ne, we have the Hall resistivity as a integer multiple of h by e square. And uh, here what we have, in addition to the Hall resistivity, which changes in a step-like manner, we also see that the voltage which is across the direction of the current, they show a periodic oscillatory pattern because of the this quantization. So, and also this is about the we can have a quantum integer quantum Hall effect, or we can have a fractional quantum Hall effect. When we say about the integer, we are considering the single electron system, but in reality we also have many electron systems. So because of the interaction between the electrons, instead of integer quantum Hall effect, we'll see a fractional quantum Hall effect, which is also reviewed in this paper. In addition to that, what was happened in the last in the year 2005 is that initially we see the quantum Hall effect only in a medium where we apply the strong magnetic field, and also there should be a low temperature. But it has been found that graphene, if you use graphene, then it's possible to see the quantum Hall effect in even in the room temperature. So this is the schematic of this Hall bar that is used to see the quantum Hall effect in graphene. So if you see the resistivity, it is also changing in a step-like manner. Also, the longitudinal resistivity, it is showing a oscillatory behavior. And one thing we can notice here is that if you consider the classical quantum Hall effect, the longitudinal resistivity, it remains always constant, like rho xx or rho yy or rho zz. It is always remains constant, which is m by n square tau. But in the quantum Hall effect, it's possible that the longitudinal resistivity becomes zero. So if you see this plateau region, so for this plateau region, the resistivity, the longitudinal resistivity is almost zero, and this is because of the mechanism that for this plateau region, the bulk of this material become insulating. So there is no electrical current that will flow through the bulk. Only the edges of the sample will support the electrical flow. So because of insulating bulk, there will be no scattering of this electron. There will be no back scattering. And so because of that, we'll see that the longitudinal resistivity will now become zero in the plateau region. So in the third figure, we have the quantum Hall effect in the graphene that we see in the room temperature. So if you see this graph, we can see the one is for the electron and one is for the whole case, the graph. So the resistivity, it shows it is quantized, and it is so a plateau region for in the order of h by 2e square in the graphene case. In the third figure, this is also the graph between the resistivity and the longitudinal resistivity and the transverse conductivity. So the plateau region is feasible, which is in 2 times of e square by h, also minus 2 times of e square by h. And if you see the longitudinal resistivity, so it is 0 for the plateau region, and it shows a oscillatory behavior. So because of that, we and also the resistivity of different graphene sample using different design. These are measured, and the error bars also calculated for different kind of sample. So for this, the errors are quite less. It is in the order of nano. So that is why we can use this to as a to use it as a standard to measure the resistance. Okay, so this is all about the concept that we have seen in week 3. So now we'll solve a few numerical problems related to this concept. Also, the last week we are left with few 2 to 3 question were remain on. So we were not able to solve it. So let us try to solve it first. Then we'll move on to solve the question that is related to week 3. Okay, so we start. So this is about the concept from week 2. So question says the acceptor like state, whether it is neutral when it is filled with an electron or it is positively charged regardless of this occupancy, or it always donates electron to the valence band, or it is neutral when it is empty or becomes negatively charged when it captures electron. So, according to you, which of this following is true for a acceptor like state? So, let me give you few minutes so that you can just uh, try to recall the concept and try to find out the answer for this. So, if you recall, acceptor-like states are those states which lie close to the conduction band and they accept electron from the conduction band and becomes negatively charged. So that means these are the, if you look at option A, these are neutral when it is filled with electron, which is not possible because it accepts the electron. So that means it was initially it was neutral, and when it accept the charge carrier, it becomes negatively charged. Option B, it is positively charged regardless of the occupancy, which is also not the case. Option C, it always donates electron to the valence band, which is also not true. Option D, it is neutral when it is empty and becomes negatively charged when it captures electron, which is true. So the answer for this question is option D. I think it was there also in the weekly assignment. So let us move to our next part. So it's given in an N-type semiconductor if the surface states capture electrons from the bulk, then how do the energy bands, which are conduction band and the valence band, behave as they approach the surface? Option A, they remain perfectly flat. Option B, they bend upwards. Option C, they bend downwards. Option D, only the conduction band bends while the valence band remains flat. Which of these following is true for the N-type semiconductor surface state? So if you recall the concept, whenever we have an N-type semiconductor, there will be diffusion of the electrons from one side of this semiconductor to the metal or the surface that we have on the sample that we have at the surface. So what will happen? There will be a depletion region that will be created at the surface because of the charge carriers. And this depleted region, they will increase the potential of the system at the surface. So in the bulk, the bands will remain as it is. But when it moves toward the surface, because of this charge buildup, the potential will now increase for the N type. So they will bend upward. And to maintain the band gap, the valence band also, it also bend upward. So that means both the conduction band as well as the valence band, they bend upwards at the surface of N-type semiconductor. Similarly, for P-type, they will bend downward. And this is question number 10. In the next question, we have a N-type semiconductor metal Schottky contact, and it's given that the metal work function, which is phi m, it is 4.5 electron volt, and the semiconductor electron affinity, it is also given chi s, which is 4 electron volt. Then you need to find out what is the Schottky barrier height given this information. There are four options. Option A 8.5 electron volt, option B 4 electron volt, option C it is zero point 0.5 electron volt, or option D it cannot be determined using this data. So let me give you a few minutes. Try to solve it by your own. Then I will show you the steps. Okay, so let me go through the steps. So if you recall, if you have a metal semiconductor contact in type semiconductor, so the electron will diffuse to the metal side, and the charges, there will be a depletion region which will uh, which is a immobile region where no further charge movement will take place. And in terms of band diagram, we can write it as, let's say this is the vacuum level, and this is the Fermi level for the metal. Now we have a semiconductor valence band. This is the conduction band. This is n-type, so EF will be close to the conduction band. And the gap between the Fermi level to the vacuum, this is the work function of metal. And for semiconductor, this is the work function of semiconductor. And the distance, the energy difference between the vacuum and the top of this conduction bandage, this is affinity, electron affinity. So to find out the Schottky barrier, so what we mean pictorially. So because of this charge movement, so there will be a quantum well that will be created. The n-type band will bend upward. The depletion region will be created this side, and there will be built-in potential, which is V0, which prevent the charge flow from the semiconductor to the metal side. Also, there is from in the metal side, there is a barrier, which is Schottky barrier, which prevents the movement of charge, the electron from the metal to the semiconductor side. So phi 0, this is the built-in potential. We can write it as phi m minus phi s, the difference between the work function. And the Schottky barrier height, we can write it as, this is phi m work function of metal minus the electron affinity of this semiconductor, n-type semiconductor. So these two values are directly given in the question. It's given the work function of the metal is 4.5 and chi s is 4. So that means the Schottky barrier height phi b, it will be phi m minus chi, which is zero 0.5 electron volt. So answer will be option C. Let us move to our next problem. In the next case, we have a gallium arsenide and aluminum gallium arsenide heterojunction, which is formed, and it is given that the electron affinity of gallium arsenide is 4.07 electron volt. Electron affinity of aluminum gallium arsenide, it is 3.65, and the band gap of gallium arsenide is 1.42. Band gap of aluminum gallium arsenide is 1.8 electron volt. So using this information, you need to calculate what is the conduction band offset and what is the valence band offset. So let me give you some time, calculate it first, then we'll go through the solution. Try to recall what are the relation between the conjunction band offset and the band gap electron affinity. Then from that you can easily calculate what is the band offset for both conduction band as well as the valence band. Let me solve it. So to calculate the conduction band offset, if you recall, it is nothing but the difference between the electron affinity of this heterostructure. So this is chi2 minus chi1, chi gallium arsenide minus aluminum gallium arsenide. So for gallium arsenide, this is 4.07 electron volt, and for all gas, we have 3.65 electron volt. So that means the offset in the conduction band, uh, where the band will bend, that length it will be 0.42 electron volt. This is the conduction band offset. For valence band offset, if you recall, this is given by chi1 plus ej1 minus chi2 plus ej2. And if you rearrange it, this is chi1 minus chi2 plus eg1 minus eg2. Chi1 minus chi2, it is nothing but the negative of conduction band offset plus Eg gas gas and Eg gallium arsenide. So minus of delta is minus 0.42 plus the band gap for this is 1.8, 1.42. So this will give minus 0.04 electron volt. So the conduction offset in conduction band is 0.42 electron volt, and offset in valence band it is minus of 0.04 electron volt. Let us move to our next question. So now we'll start solving the conceptual as well as the numerical problem related to week 3. So the first question is, which one of the following correctly represent the steps of a photolithography fabrication process? First one is exposure followed by coating, then etching, develop, stripe, metallization, and etching. In B option, it is coating, exposure, develop, stripe, etch, metallization, etch. And option C, we have develop, then coating, exposure, stripe, etch, metallization, etch. And in the option D, we have coating, exposure, develop, etching, stripe, metallization, and further etching. Which one of this you think is the correct? So if you see option D is quite close to this process of photolithography. First, we coat the substrate with the photoresist. Then we expose it to the optical radiation. Depending on the kind of photoresist, different types of pattern will be developed. Like for positive photoresist, the exposed area will be removed, and for negative one, the unexposed area will be removed if you dissolve the sample in a solvent. This is the developed stage. Then we can etch it further to define our design. Then we remove the excess, we can remove the stripe, we can remove the resist layer. Then we can go on to do the metallization and also further etching. So answer is option D. In question number 2, it says, which of these following is true for the modes of the photolithography? Option A, diffraction effects affect the accuracy limit of pattern transfer in the projection mode photolithography, but not in contact or soft contact mode photolithography, which is not true. Diffraction effect is there for both the contact mode as well as the subcontact mode and the projection mode. In contact and subcontact mode, we have the near field diffraction, and for the for the projection mode, we have the far field diffraction. So for both the cases, the accuracy limit of pattern transfer will be affected by the diffraction effect. Option A is not the correct answer. Option B, projection mode photolithography offer pattern transferred with high resolution limit. Okay, so if you compare the three types of photolithography, like one we have seen is the contact mode, another one is soft contact mode or the proximity mode. Another one is the projection mode. For this contact mode, we have the resolution limit in the order of 0.5 micrometer. For soft contact, it is in the order of 1 to 2 micrometer. And for projection mode, it is in the order of 0.007 micrometer. So that means when we do the pattern transfer, the resolution for the projection mode will be higher in projection mode. So that seems option B is the correct one. But let us see what we have in option C and D. In option C, the minimum feature size in proximity mode lithography is independent of the wavelength of the incident radiation, which is not true, right? If you recall the proximity mode, the minimum feature size that can be patterned or that can be resolved, it is given by root over of k lambda g. So that means it depends on the square root of this wavelength. So option C is not correct. Option D is it's trivially not correct because it says none of the above. So the correct option for this is option B. Okay. For question 3, it is also a conceptual problem. In the quantum ballistic transport regime, the condition for observing the ballistic transport is whether the device length should be greater than the phase coherence length, which is not true. In option B, we have device length less than the phase coherence length, and the Fermi wavelength, it is in the order of the device length. That means, which is true for the quantum ballistic transport. So option B is the right option. Option C and D, these are obviously not the case. So answer will be option B. Question number 4. In projection photolithography, the mask image is in direct contact with the regist, or it is projected and then demagnified, or it is magnified 1 to 1, or it is not used. Which one of these you think is the correct option? So if you recall the projection mode photolithography, so we project the image of the mask on the photoresist using the optical system. And so that means for projection photolithography, this option B will be correct option because it is in options A says it is in direct contact with the regist, which is not the case. Option C is magnified 1 to 1, which is also not the case, and option D it is not used, which is not correct. So answer will be option B. Question number 5. It says a certain photolithography, which is a projection mode photolithography process, uses a wavelength of 365 nanometer and a numerical aperture of 0.85. If the minimum size required is 100 nanometer, determine whether this is theoretically achievable using this excitation condition. That is, if you use a wavelength of 365 and numerical aperture of 0.85 in a projection mode lithography, then will it be possible to get a minimum size of 100 nanometer or not? So let me give you some time. Please try to solve it first. Then I will show you the detailed steps. It's quite easy if you know the relation between the minimum size and the parameters that is given, lambda and numerical aperture, then you can directly see whether it is possible to get a size of 100 nanometer or not. Try to solve it. I will show you the steps in the meantime. So if you recall the projection mode photolithography, the minimum size it is decided by the average limit, which is W minimum. It is given by K1 lambda by Na. So let us see using the excitation condition that is given, what will be the W minimum that we'll get. So K1 is 0.75, lambda is 365, numerical aperture is 0.85. So this will give a value of 322 nanometer. So this is the minimum feature size that can be patterned or that can be resolved using this projection mode photolithography. But the question asks if the minimum size required is 100 nanometer, Determine whether this is theoretically achievable using this setup, which says because here the double minimum is 322 nanometer, which is quite larger than 100 nanometer that we want to get. So that means if we use this setup, we use this wavelength numerical aperture, or then it's not theoretically possible to get uh, a feature size of 100 nanometer. So to get the feature size, either uh, the best practice is to change the numerical aperture. So if you recall numerical aperture, it is given by n sine theta. So we can change the refractive index, and we say this is immersion photolithography. So if you change the refractive index, then it's possible to change the feature size. So this is one of the way that you can do, or you can also change the wavelength. If you go from go to the deep UV wavelength or extreme UV wavelength, maybe it's possible to get a double minimum of 100 nanometer. So the answer is no, it's not possible. Question number 6, it says estimate the resolution and the depth of focus of a state of art excimer laser stepper using a krypton fluoride light source where lambda is 248 nanometer with a numerical aperture of zero point 0.6. Assume that K1 is 0.75 and K2 is 0.5. So we have a source, an optical setup, and it's given that the lambda is 248 nanometer and the numerical aperture is zero point 0.6. Also, it's given K1 is 0.75, K2 is 0.5. Then what will be the resolution and the depth of focus? Try to calculate it first, then we'll go through the detailed solution. So if you recall the formula for resolution, it is given by K1 lambda by Na, and the depth of focus, which determine the vertical resolution, it is given by K2 lambda by Na square. So you just need to put the parameter here to get the answer to this question. So K1 is given 0.6, sorry, 0.75. Lambda is 248, Na is 0.6. And this will be 0.31 micrometer. And for TOF, this you can take it. K2 is 0.5. This is 248.6 square. So this will be 0.34 micrometer. Just check it whether you are getting this answer or not. So resolution will be around 0.31 micrometer or 310 nanometer, and the depth of focus will be around 340 nanometer. Question number 7. Which of these following plot correctly represent the relationship between the gap size and the feature size in the proximity mode photolithography? This is quite easy if you recall W minimum, which is here it is given F. This is given by square root A lambda G. So that means F is directly proportional to square root of J. So square root dependence is option B. Question number 8, it is also quite easy. It's directly conceptual based. Which of this following is true for the mobility of charge carriers at room temperature in a silicon sample? Whether the mobility of hole is greater than, it is less than electron, or it is greater than electron, or it is equal to electron, or it cannot be determined. So if you recall the mobility formula, it is given by E tau by m star. So mobility, it is inversely proportional to the effective mass of the charge carrier. And for hole, the effective mass is less than the effective mass of electron. So that means the mobility of hole is greater than mobility of electron. So answer is option B. Question number 9. Which of this following is true for electron beam lithography? Option A, secondary electron are most commonly used for the lithography techniques, which is true, right? And option B, resolution is mostly determined by the wavelength of the electron, which is not true because the resolution is for electron beam lithography, it is mostly decided by the lateral diffusion of secondary electron and forward scattering, Regis properties. So this is not quite true. Option C, surface topography can be accurately observed using the backscatter electron. This is not good. This is not correct because the surface topography, it is decided by the secondary electron. So if you collect the secondary electron, it's possible to observe the possible to see the surface topography. And I will Option D is also not correct because it says all of the above. So answer is option A. Question number 10. For a projection mode photolithography with lambda is 193 nanometer and K2 is zero point 0.5, zero point 0.4 and numerical aperture it is given 0.85. The depth of focus for this case is sigma. If the wavelength is reduced to 13.5 nanometers, now we are reducing the wavelength to 13.5 and numerical aperture is reduced to 0.33. K2 remains the same, it is 0.4. Then by what factor does the depth of focus will change? So we need to see the relation between sigma prime and sigma, how these two are related. Whether the sigma prime increases by 2 times, decreases by 2 times, or it decreases by 10 times, or it increases by 5 times. So calculate it and try to get the answer, then I will show you the steps. It is also quite formula based. If you recall the formula for the depth of focus, then you can get the answer. So if you recall the relation, the depth of focus, it is given by K2 lambda by n square. So that means the degree of freedom, which is sigma directly proportional to lambda by n square. So just put the parameter that we have. So if we divide sigma 1 by sigma 2, this is sigma 1, sigma 2. This will be lambda 1 by lambda 2, Na2 by Na1 square. Lambda 1, lambda 2, Na1, Na2. We have 193 divided by 13.5. Na2 is 0.33 and Na1 is 0.85. So this will give, I think, 2, approximately 2. So that means sigma 1, it is 2 times of sigma 2. So when we change the lambda 1 and Na1 to a value 13.5 and 0.33, we see that the depth of focus will decrease by half of its initial value, decrease by 2 times. So that means the answer would be option B. So it is decreases by 2 times. Sigma 2 is sigma 1 by 2. Okay. Question number 11. An extreme ultraviolet lithography uses lambda is 13.5 nanometer, numerical aperture 0.33, and K2 is 0.25. And another, there is a deep ultraviolet system, which is lambda is 19.3, sorry, 193, numerical aperture 0.93, and K2 is given 0.25. Then what is the ratio of minimum feature sizes? What is this ratio? This is, see, this is also formula based. If you recall, W minimum is directly proportional to lambda by Na, right? So you can write it as lambda DUV, lambda B multiplied by Na of EUV and Na of DUV. DUV is 193 nanometer. This is 13.5 nanometer. Numerical aperture of extreme ultraviolet 0.33. Deep ultraviolet 0.9. So this will give a value of, I think, 5.1. Option C. Question number 12. For a proximity lithography, if given K is 1, lambda is 365 nanometer, and G is the gap between the mask and the wafer, then what is the maximum level gap G max if the desired feature size is 500 nanometer? So if you recall it, recall the formula, W minimum, it is given by K1 lambda by Ne. Mm, Sorry, this is for proximity, right? For proximity, we have K lambda G. K is 1, so this is lambda G. Lambda is 365 and G is not given, but double minimum is given, it is 500. So that means G will be 500 square is 65. So this will give a value of 685 nanometer. Option C. Next question, it's a continuation of question number 12. It says if the gap in the above case is increased by 20%, by what percentage does double minimum will increase? So we are increasing the gap by 20%. Then what will be the percentage change in double minimum? This is quite easy. So previously we get a gap size of 685 nanometer. So gap size is increasing by 20%. That means G prime will be 1.2 times G. So this will be 822 nanometer. So this is the new gap size. The change in the gap size when you change the gap between the silicon and the wafer. So because of this, the resolution limit will also change. So new feature size, double minimum. This will be square root of k lambda g. K is 1. Lambda is also not changing, 365. So, and g is g prime, which is 822. So this will come around 547.7 nanometer. So that means previously we had a feature size of 500. It was 500 earlier. Now we have a feature size of 547.7 nanometer. So the percentage increase will be this. I think you already know. This is how you can calculate the percentage change. So second is 547.7 minus 500 by double minimum 1, 500, which will be 9.54 percentage. So answer will be option B. So the gap size, the feature size will increase by 9.54%. Question number 13. According to the classical Hall effect, which of these following graph correctly represent the variation of resistivity under the application of external transverse magnetic field? So it's a variation of the longitudinal resistivity, which is rho xs, and also the transverse resistivity, how they will be changed, how they will behave when you apply external magnetic field. Whether the transverse will remain constant or the longitudinal will increase linearly. This, if you recall, this is not the case. So we need to recall the tensor in the presence of the external magnetic field, which is rho xs, rho xy, rho ys, rho y. rho x's and rho yy, it is m by n squared tau. This remains constant in the classical case, because in the classical case there will be scattering because of the scattering center. So that is why we'll always see that the current is resisting. Now for the off diagonal term, rho xy, which is minus of rho yx, this is b by n. So this off diagonal term is the Hall resistivity, or we say transverse resistivity. This is directly proportional to B. So that means the longitudinal one is independent of B. It will remain constant. And the Hall, the off diagonal one, they will increase linearly. So the option is question number D will be the correct representation of a change in resistivity in the presence of magnetic field when we consider the classical Hall effect. Question number 14. There is a copper stripe of 2 centimeter wide and 1 millimeter thickness. It is placed in a magnetic field with B equal to 1.5 Weber per meter square. Perpendicular to the stripe, it is the transverse magnetic field is applied. Suppose a current of 200 ampere is set off in the stripe. What is the all potential difference that would appear across the stripe? If you consider that the carrier concentration is 8.4 into 10 to the power 28. So this you can calculate as VH, you can write it as I RH, or I the Hall resistance, you can write it as Hall resistivity L by A, or you can further simplify it. Rho H is V by N L by LT. So the Hall potential difference, it is given by V I by N E T. So these are given. B is given, it is 1.5 Weber per meter square. I is given 200 ampere. And the carrier concentration is 8.4 into 10 to the power 28 electronic charge. And T is 1 millimeter. So this will give a value of 2.2 into 10 to the power minus 5 volt. So this amount of Hall voltage will appear if you place this Hall bar in the transverse magnetic field. Okay, so we'll stop here for today. There is only 2 questions remaining. We'll try to solve it in our next live session. So in the next part, we'll try to cover some mathematical relation, also some what are the effects of quantum Hall effect on energy level. So we will go in details and we'll solve the problems that is related to the concept of weak foot. So please try to attend the live session. This will be on Friday, same time from 6 to 8. So let us meet on next Friday. Goodbye, everyone.